everyone, I hope you're all staying healthy and safe during this quarantine. And today I'll be covering question number 3 of the 2015 AP Chem exam. And this question has 6 parts. The topics covered on this question include net ionics and knowing your solubility rules, acids and bases, titrations, dissociation, and it's definitely like knowing like Ka, pH, graphing with titrations. So for part A, it says write the net ionic equation for the reaction between potassium sorbate and hydrochloric acid, which are both aqueous. So first we have to get the ionic equation. If you take the two and just rewrite them, which I am doing right now, you'll get KCl plus HC6H7O2. And using your solubility rules, we know this is soluble and this is insoluble. So, okay, since these are also soluble, as given to us in the problem, we can break all of the soluble ones up into ions. And keep the insoluble one as is. Okay, so on both sides of the equation, there are spectator ions, and they're not reacting with anything essentially. So what we can do is cross them out, and your result is H plus C6H7O2, which is reversible to HC6H7O2. And this is your net ionic equation. So since this is just one point, you have to make sure to get the plus and the minus charge of both reactants, and then just to write the net ionic properly, making sure you don't have any spectator ions in there. It's just 1 point. So part B reads that a total of 29.95 milliliters of 1.25 molar hydrochloric acid is required to reach the equivalence point. Calculate the concentration of potassium sorbate in the stock solution. So the equivalence point is when all of the potassium sorbate has reacted with the acid, the titrate. So the exact number of moles that we get of potassium sorbate has to be equal to the acid, which is hydrochloric acid. So what we do first is get the number of moles of hydrochloric acid, which we have based off the equation that 1.25 molarity is equal to 29.95 milliliters over 1,000, because you have to convert it into liters, equals X moles of HCl. After we get that X is equal to 0.0374 moles of hydrochloric acid. Okay, so what do we do now? We have these 0.0374 moles, which we go like this. And this means that there's 0.0374 moles also of C6H7O2 minus. And then what we have to do after is make it back into molarity. So how much do we have originally? We have 45 milliliters. So if we take it over 45 milliliters and then divide by 1,000, we get 0.832 molarity. And this is the molarity of stock solution. This question's 2 points. So first we have to show how we get the number of moles of HCl at the equivalence point, and then the second point is getting the correct answer. So this is your first point, and this is your second one. Part C reads that the pH at the equivalence point of the titration is measured to be 2.54. Which of the following indicators would be the best choice for determining the endpoint of the titration? Justify your answer. So here we have 5 different indicators, and they all have different pKa's. So how do we know which one to use? We look at all the different pKa's, and we want the one that's the closest to the pH, so it changes colors at approximately the same area. So obviously we're going to look for the closest one, which is thionyl blue. This question's only 2 points, so what we have to do is justify our answer and also say the right thing. So it'd be thionyl blue. And it's going to be the best choice because, so that's our first point. And it's going to be our best choice because because it's pKa is the closest to the pH at the equivalence point. So the color change will be around the equivalence point. And this is our second point. So here you just have to explain why, and that's because it's changing colors at around the same area as the equivalence point, and pick the right one, which is obviously thermal blue because it's the closest to 2.54. So part D reads, calculate the pH at the half equivalence point. So at the half equivalence point, we know that the concentrations of potassium sorbate and HCl are equal because half of potassium sorbate has been titrated. So what we do is we use the Hasselbalch equation, which is pH is equal to pKa plus log of A minus over HA. But these two are equivalent, right? So what does that mean? It means that log of x over x is equal to log 1, which is equal to 0. So pH is equal to pKa. And we already have the Ka value. It's 1.7 times 10 to the negative 5. This is given to us originally. And we have to get the negative log of it to get the pKa. And that comes out to be approximately 4.77. And that's your pH. So for part B, that's all you have to do. And it's only 1 point. So you just get the point if you write the correct pH. And there's no units here for pH. Part E reads that the initial pH and the equivalence point are plotted on the graph below. Accurately sketch the titration curve on the graph below. Mark the position of the half equivalence point on the curve with an X. So, what do we have to do? First, we have to find the half equivalence point, which we've already calculated the pH for in part D, which was 4.77. But where do we put it? We have to put it in between this here and here. This is about 29.95, so we have to put it a bit less than 15 because it's at half that's been used. So if we look around here, this is 4, I'd say like right about here, it's our X. And we're starting here with some base, and it's gonna go like this, and then that, and like this. Just continuing it a bit. And this question is 3 parts. So the first part is that we have to have, or 3 points. So the first point is that we have to have the correct half equivalence point at approximately like in between 14 and 15. And then we also have to have the right pH, which we've calculated before, so that's just 1 point. So plus 1 right here. And then our second point is that the curve has to level off through the half equivalence point. So like this essentially. So that would be our second point as well. And then the third point is to have a steep slope at the equivalence point. So that's it for me. The part F reads that the pH of the soft drink is 3.37 after the addition of potassium sorbate. Which species, HC6H7O2 or C6H7O2 minus, has a higher concentration in soft drink? And justify your answer. So this question's only 1 point, but there's 2 different ways of looking at it. I'm going to show you both ways. The first way of looking at it is taking your Ka, and we know that's equal to H plus and times C6H7O2 minus over HC6H7O2. And that's because HC6H7O2 can dissociate into H plus and C6H7O2 minus, like this. And we always put the products on top and the reactants on the bottom. And we already have some of these values. Ka is equal to 1.7 times 10 to the negative 5, and H plus over here is equal to 10 to the power of negative 3.37 because 3.37 is the pH. And if you remember, we get pH from taking the negative log of H plus. And so then H would be doing it to the opposite, which would be putting 10 to the negative pH. So then we can plug these values in. And I'm just going to bring this over to the other side so we can compare them. And when we divide the two, we get about 0.04. And so what does that mean? It means that the 1.7 times 10 to the negative fifth is about 1/25 times this one, which means that HC6H7O2 must be greater than C6H7O2 minus, because its value at the bottom is much higher than the one on top. So that's one way of doing it, mathematically. And I'm also going to show you a second way, just because sometimes it's easier to explain than words. We have these two. They must be equal. At the half equivalence point, because that's when the two concentrations are usually equal. And then that's at a pH of 4.77. But pH of 3.77 is lower, right? And if we look at the graph from before, I'm going to bring this, it means it's past the half equivalence point, which obviously means that we have more HC6H7O2 minus, because we've gone past the point where they're equal and we started out. So we started out with more than, if we remember our initial equation for the net ionic. But after we get to the equivalence point, we're going to end up having more HC6H7O2 than C6H7O2 minus. And if we wanted to write this all in words, what we would say is that the concentration of HC6H7O2 and C6H7O2 minus are equal at the half equivalence point. However, the pH of 3.7, 3.37 is less than the pH of 4.77, so are past the half equivalence point. So the concentration of HC6H7O2 will be greater than C6H7O2 minus. And this question is only 1 point, and it's a lot of work for just 1 point, but you have to show how you get the right answer. So it's 1 point for both the justification and showing that HC6H7O2 is greater than C6H7O2 minus. So you can either do it this way or that way, whichever is better for you.